Welcome to you for lecture number 11 of Signals and Systems. Today's topics covered are elementary signals part 3, the first one being impulse function, ramp function, and then some other signals, few other signals we'll be studying. Before we proceed to the current session, let us check the assignment problems that has been given to you in the previous session. There were two assignments given to you people. The first being the combination of the sum of shifted unit step functions, and the second being the same thing in a discrete time. The continuous time function, the first problem goes like this: u of t plus 1 minus 2 into u of t plus u of t minus 1, which is equal to x of t. So here the sum of these three signals will get me x of t. Now we shall check how to generate x of t signal. Let us draw the unit step function first in the continuous time domain. The unit step function looks like, at 0 it will take a step from 0 to maximum amplitude, that is 1, and it continues thereafter in the positive axis of time. U of t plus 1 is nothing but it's a shifted version of u of t, wherein here you can find plus, hence it is a shifted version, left shift by 1 times. U of t, take this u of t, left shift by 1 times and maintain everything else in the same manner. That gives you u of t plus 1. It is in this manner. Whereas u of t minus 1, it is right shift by 1 time. So whatever was happening at 0, the same changes, variations happen at plus 1. Shift right by 1 time. But here we have been asked minus 2 into u of t. We already know what is the meaning of u of t. 2 times of u of t is its amplitude scaling. Amplitude becomes 2. As there is a minus symbol here, so if I just take that minus symbol, it again is a amplitude scaling. Hence, with respect to horizontal axis, it will be inverted. That is, the amplitude becomes minus 2. So now the highlighted with red color underlined signals are of our focus. U of t plus 1 is the first term, minus 2 into u of t is the second term, u of t minus 1 is the third term. So as I have already taken minus sign here, taken care, so you have to just add all these three things. To add it, let me consider the value of the signals, all these signals, to compute the resultant signal x of t below or beyond the minus 1. Minus infinity to minus 1, I don't have any signal in all these three signals, terms that has been given in your question. So there is no signal here, there is no signal on this side, there is no signal on this side. So hence, it will continue to remain at 0 until it reaches 1, minus 1. From minus 1 to 0, I am having the signal for u of t plus 1, I am having amplitude 1, u of t minus 1 is 0, minus 2 into u of t is also 0 in this range, minus 1 to 0. Hence, there is only one signal which has a finite amplitude, that is u of t plus 1. So I retain that particular signal as it is, its amplitude being 1. From 0 to 1, I have u of t plus 1 with amplitude 1. I have minus 2 into u of t also with amplitude minus 2, but u of t minus 1 has a 0 value. So hence amplitude 1 plus, because minus is already taken care, plus of minus 2. So 1 minus 2 gives me minus 1. So this goes to minus 1. It will continue with amplitude minus 1 until 0 to plus 1. So at 0 to plus 1, it will return as it is. From plus 1 onwards, u of t plus 1 is continuing in the same manner. Minus 2 into u of t is also continuing in the same manner. So if there were only these two signals, it would have been continued in the same manner till infinity. But we have addition of one more signal, that is u of t minus 1, wherein amplitude 1 will be added to this after t equal to plus 1. So if I add amplitude 1 to it, so it will take the resultant signal to amplitude 0, and it will continue thereafter. So this is your resultant signal x of t. Now in the similar fashion, we look into the next one, that is second problem. X of n is equal to u of n minus 1 minus u of n minus 5. So before we proceed with this equation or this assignment, let us draw what is u of n in diagram. So u of n is equal to 1 for n greater than or equal to 0, and it is 0 for the n value having negative. So when I ask you to find out u of n minus 1, it is shifting u of n signal to its right by 1 times. Shift u of n signal to its right 1 times. Whatever that was happening at 0, it will happen at 1. So thereafter the amplitude 1 will be retained throughout in the positive axis of n. U of n minus 5 means u of n is shifted to the right by 5 times. So whatever that was happening at 0 should be shifted by 5 times. That is, n is equal to 5. At n is equal to 5, so amplitude of u of n minus 1 signal becomes 1, and thereafter it will retain the same amplitude till the positive infinity. Now we need to subtract these two things. So to subtract these two things, you can check here in the negative axis of n, both u of n minus 1 and u of n minus 5 has got 0 value. So here everywhere it is just a 0. At 0 also it is 0 because u of n minus 1 is also 0, u of n minus 5 is also 0. But here for n value equal to 1, 2, 3 and 4, I have 1, 2, 3, 4 values for n as 0 amplitude in u of n minus 5, but here I am having amplitude 1. So what I'm supposed to do at this signal, for example, if I consider n is equal to 1, n is equal to 1, u of n minus 1 is 1, u of n minus 5 is 0. 1 minus 0 is 1. So here I'll get the amplitude 1. Similarly at 2, here it is 1, here it is 0. 1 minus 0 is 1. Similarly for 3, 1 minus 0 is 1. Similarly at 4, 1 minus 0 is 1. At 5, so let me draw that also. At 5 also you have 1, so it continues. But at 5, you have n minus 1's amplitude as 1. Here also 1. And here n minus u of n minus 5's amplitude is also 1. 1 minus 1 will result in 0. Same thing. 6 at n equal to 6 also you will be having 0. You will be having 1. 1 minus 1 will give you 0. 0. It will continue thereafter. So this is the answer for the assignment 2. Please cross check with your answer that you have done whether it's matching the answer that is in front of your screen. So quickly we'll move on to the very next topic, and a very important topic. Let me mark it as a star because it's very important. So impulse function is also called as delta function. Is a very important topic. We have a discrete time version of the impulse function as well as continuous time version of the unit impulse function. So impulse function, normally we use a word called unit impulse. Unit impulse means its strength will be 1. Its strength will be 1, hence we call it as unit impulse. The mathematical model for this unit impulse function has been shown as here. Delta of n, delta is the denotation used for impulse function. Delta of n is equal to 1 for n equal to 0 and 0 for any other value of the n. That is written in this manner. N not equal to 0 means n can have any other value other than 0, where the amplitude of the delta, the strength of the delta of n is 0. I stress upon a term called strength. I'm intentionally using it strength, or else it is called as area. So whatever you're visible here, we normally don't call it as amplitude, rather we call it as strength or area. Let me come to this point in later stage. Similarly, here for continuous time version of the unit impulse function is defined as delta of t, this is t, is equal to 0 for t not equal to 0. And whereas delta of t is equal to 1 for t is equal to 0. Let me draw that here. So delta of t, this is t. At t equal to 0, you have the amplitude as, not amplitude, strength as 1. Whereas for any other value, the value of the delta t is 0. So this is the meaning. So why I have used an integration for this delta of t is with some intention. So integration's physical meaning is finding out the area under the curve. So area under the curve of delta t gives me 1. So area is equal to 1 it is. So it has been written in the statement. Total area under the unit impulse is unity. Remember this. It's not the amplitude. We have to use this arrow mark and write it as 1, which means it's a area, or we also call it as a strength. Why it is not called as amplitude? So that's a question in front of us now. So we will find the answer for it in the next slide. So delta of t is also referred as Dirac delta function. I repeat, Dirac delta function. So now we will see some graphical representation of this impulse function. The impulses are not a function in the ordinary sense because its value at the time of its occurrence is not defined. It is represented graphically by vertical arrow. Its strength is either written beside it or it is represented by its length. Either it is written beside it or else it is written at this place. So its value when it is occurring is not defined because its value will be infinity. It is like an infinite pulse that is getting generated. Now why we are writing it as 1? That's our question. So we will find its answer in the very next slide. Before that, we just check graphically how it is represented. Delta of t, x-axis t, you put an arrow mark and mark its area or strength in this way or in this way. Both are okay. So throughout this book or this sessions of signals and system, we follow this method. And here we have some amplitude scaling as well as time shifting. 9 delta of t minus 1. Let us consider delta of t minus 1. What is the meaning of delta of t minus 1? T minus 1 is nothing but right shift by 1. So this delta of t, I'm shifting it by right. So it is 0. So if I shift it by 1 time, so at 1 it will appear. And what is its amplitude? Its amplitude is 9. But I said it's not an amplitude, rather it's an area. Hence we call it as area scaling. We call it as area scaling rather than amplitude scaling. Similarly, here delta of t plus 2. How do we write delta of t plus 2? T plus 2 is nothing but left shift by 2. Left shift by 2 is written as this manner. We have t here. So if I shift delta of t by 2 times onto the left, it will come at minus 2. This is how it is written. And thereon, I have area scaling again with minus 3. So if I take its minus 3, so inverted with respect to time axis with a amplitude minus 3. That is what is given here. So remember one thing, integration of delta of dt into dt will result in 1, which is nothing but area. So we are throwing more focus on this concept in this slide. So x delta of t is some signal which we have taken for the analysis, which we in turn related to delta of t. X delta of t is the zoomed version of delta of t. For example, if this is delta of t, this is t is equal to 0. This is delta function which with its strength 1. This is zoomed a lot. Zoomed and zoomed and zoomed, I can see this particular curve. If I zoom it still more, this is what will be visible for me. If I zoom still more, this is how it will be visible. Okay, so to just having some conceptual idea, I have taken this. Okay, so to this figure, to arrive at delta of t, we get equation, mathematical equation in this fashion. Limit, we apply a limit. Delta tends to 0 because minus delta by 2 and plus delta by 2 are the lower limits and upper limits here. So this is a width of this rectangular pulse which we got after zooming this impulse function. So this delta, as it tends to 0, as it tends to 0 means this will approach 0. This will approach 0. As delta tends to 0 in the signal x delta of t, we get delta of t. That's very simple. Please remember this equation for this session. So I'll take this reference of this equation in future. Okay, so this we got, I can write this side. This we got by zooming at this place. I have to zoom it and I get this. Hope it is fine. Now, how come area is equal to 1 though there is a change in the width and length? That is a point that we need to analyze now. So here what we are doing is area's formula of a rectangular is length into breadth. So if length is this is length, this is width or breadth, I can say. Breadth is delta, length is interchangeably I can use. Breadth should be 1 by delta. So here the amplitude will be 1 by delta. So when it cancels, it will result in 1. So this is a funda what we have to understand. Okay, so delta of t, if it is zoomed, it will look in this fashion. So the width is delta, amplitude is 1 by delta, its area will be 1. Area will be 1. Okay, so limits, to throw more focus on this, let me take one simple analogy. You know that length into breadth is equal to area. Now if I have length equal to 1 and breadth equal to 1, so the area value will be, yes, it's 1. If I increase the length, I want my area to be 1 itself. So what should be the breadth? If I want to retain my area is equal to 1, what should be the breadth? It should be 0.1. Similarly, if I have 100 here, this should be 0.01 to keep area is equal to 1. If it is 1000, here it is 0.001 to keep its area is equal to 1. If it is infinitely large number, then to keep the area is equal to 1, it should be very less number. So infinite into 0 will give me 1. The meaning of length I had said itself. Okay, this says length, this says breadth, sorry. So if length is equal to infinity, breadth is equal to 0, still I get area is equal to 1. Breadth is equal to 0 means what is the breadth here? It is almost overlapped on the 0 axis. So the breadth is 0 here. So length should be infinity. That is what is the amplitude. So infinity into 0, actually mathematically it is not a number, but conceptually I'm trying making my this concept understandable for you. So its area is equal to 1, strength is equal to 1. Unit step and unit impulses in the slide, wherein the unit step and unit impulse are nothing but unit stands for amplitude 1 or strength 1. Here it is amplitude, here it is area or strength. As a approaches to 0, g of t approaches to unity. So here it is g of t. I said nothing happens instantly in practical. So step function, take a step at 0. So you were writing it in this fashion, right? U of t, amplitude 1. But this instantly nothing happens practically. So there should be slight delay. So that delay has been mentioned here. From minus a by 2 to plus a by 2, it will take time to rise to the amplitude 1. So to tell it, this is the width a. As a approaches to 0, g of t approaches to unity. That's the meaning. And g dash of t is written here. So this is in the same manner as a approaches to 0. This will be unit impulse. Strength becomes 1. So here there is a statement. Please read it carefully. Unit step is the integral of unit impulse, and the unit impulse is generalized derivative of the unit step. The meaning is delta of t is nothing but derivative of u of t is here. Derivative of u of t. Delta of t is nothing but differentiation of u of t. Differentiation of u of t. So this is u of t. This is u of t. So from here to here, what is the variation? The variation is 1. So that's why you are getting it as 1. Okay. So differentiation of u of t will give you delta of t, and integral u of t is given by integral, running integral, I can say integral of delta of tau d tau. Very important. We shall look into the properties of the impulses now. So here there is the same formula that I had wrote in the previous slide has been taken over to give more insights. Delta of t is equal to d of dt, d by dt of u of t. So here u of t has been taken here. U delta, why I have written delta? Because it's been zoomed. I'm able to see the delay that has been caused at step. So it's not impossible to see it practically, but there will be some delay here. So to witness this delay, this is 0. So it has reached amplitude 1. Now let us go in detail here. Change in the time. Change in the time. That is, let me call this as T1, this as T2. At T1, what is the amplitude? We write it as A1. At T2, what is the amplitude? I write it as A2. So from T2 minus T1, that is in this range, T2 minus this range, what is the change occurred? A2 minus A1. That much is a change in the amplitude. For the change in the time from T1 to T2, what is the change happened in the amplitude? That is what we are measuring. That's the physical meaning of the differentiation. So A2 being 1, A1 being 0, T2 being delta, T1 being 0. This is 1 by delta. That's it. That is the amplitude. Amplitude of the delta signal is 1 by delta. That is what we got. Differentiation of ut will give me the delta of t, its amplitude. And here we write it as 1, that is your area or strength. And if we write 1 by delta, it is the amplitude. Remember this. And similarly, this equation also I have taken over again to give more insights. U of t is given by running integral from minus infinity to t, delta of tau into d tau. It's a running integral. Tau is a time between the delta, the constant. Tau is a time between the delta. So it's a running integral. So as the integration, the area under the curve of the delta, if you take, that always gives you 1 as an area, and 1 being the amplitude of the u of t. This is 1 for t greater than or equal to 0. So these two formulas are togetherly make the first property of the impulse function. This is how these two are related. A relation between delta function and unit step function. And the second property being the delta of t is an even signal. Why it is even signal? Because when I zoom it, the delta function looks like this. So minus delta by 2 plus delta, I am having the width delta. The amplitude is 1 by delta, its strength is 1. This is what we have understood. This is being delta of t. So here, if I just break it in terms of two halves, the positive half and the negative half looks alike, looks in the same manner. Hence, we call it as a symmetric signal. This is a symmetric signal. So symmetric signals, all symmetric signals are even signals. How it is written? Delta of minus t is equal to delta of t. So at my negative side also the amplitude looks same. The positive side also the amplitude looks same, irrespective of t's value, whether it is positive or negative. Hence it is a even signal. Delta of t is a even signal. Remember this. The third property being a very important property, the integration of or integral of delta of t into dt will give you 1, and that 1 is area or strength. It's not an amplitude. It's not an amplitude. Delta of t's integration will give you area under that curve. Area under that curve is 1. And if I multiply a constant to the delta of t, and if I take its integration, k is taken out. So when I take k outside, integral of delta of t dt gives me 1. 1 into k will give k. This is area scaling. I'm not scaling the amplitude, I'm scaling the area. Again, an important points to remember. Area scaling it is. So k into 1 will give you k. The fifth property being x of t into delta of t. Whenever you multiply x of t with delta of t, it is as good as writing x of 0 into delta of t. Because let me take one example, rough example. Think that this is x of t. This is x of t, and there is some variation like this in the signal. Some random signal I have taken, and there is a delta of t looking in this manner. At t equal to 0, I am having area 1. So when I multiply this x of t with delta of t, you just check. At t is equal to 0, I am having finite value of delta of t as well as finite value of x of t. So this into this, both are non-zero number, I'll get a non-zero value. Whereas you take any other value of t, negative side or positive side, the amplitude of delta t is 0. So 0 into anything will give you 0 itself. So hence, at t is equal to 0 alone, your signal will result in non-zero value. Hence, x of t into delta of t will result in x of 0 only. What is the meaning of this? X of 0. This value is x of 0, constant. X of 0 into delta of t. That's the meaning. So here the explanation has been written. Delta of t is equal to 1 only at t is equal to 0. So x of t value is non-zero only at t is equal to 0. That's why we write it in this fashion. Okay, so this is first part of fifth property. The second part of the fifth property is here. If I take its integration, let me assume t naught is equal to 0 right now. T naught is equal to 0 right now. X of t delta of t. If I write it in this fashion, the integration if you take, then it will result in x of 0, because I have told you t naught is equal to 0. It means it will result in only x of 0. For example, if I take its integration, x of 0 is a constant, take it outside. Integration of delta t is its area under the curve. It is area is equal to 1. 1 into x of 0 is x of 0 itself. So in place of t naught, I am having 0. So that's why I have got 0 here, x of 0. In place of 0, if I write any other value, so let us consider t naught, it will be x of t naught. So this general formula is called shifting property or sampling property. Please focus here on the spelling S-I-F-T-I-N-G, shifting property or sampling property. Why it is called sampling property? Because this delta of t helps us in order to extract the sample of the given signal. X of t being the real-time signal, if I want to extract the sample of it at every time sample that has been mentioned by the user, so I will fetch this when delta of t, I'll fetch this when delta of t minus 1, I'll fetch this when delta of t minus 2, like that. Wherever I want, I can fetch its value by using this property. Hence, this is called shifting or sampling property. Very important property. So to focus more on it, I have taken the continuation, sampling and shifting property. The sampling property extracts the value of a function at a point. That is what I explained just now. And here I have taken an explanation. In place of x of t, I have written just g of t. G of t naught, what I get. So as I explained in previous slide. So in here, just observe this. You just observe this. Fifth property, the first part, x of t delta of t will give you x of 0, because t minus t naught, t minus t naught, t naught is 0, x of 0 here. Similarly, g of t delta of t minus t naught is g of t naught, g of t naught. Delta of t minus t naught as it is, you need to write. So g of t naught is some amplitude value of that particular sample extracted. So hence you need to take it outside the integration. So g of t naught t naught have to be written here. So rest of the things put it in the integral, minus infinity to plus infinity, delta of t minus t naught dt. So delta of t minus t naught dt is 1. You already know it. So whatever integration you do on delta, so that will result in area is equal to 1. And t minus t naught, it has been already taken care, because so delta will be 1 For example, delta of t minus t naught will look like this. This is t is equal to 0. This is t is equal to t naught. So here it will be 1. So at t naught, whatever value will be there, that will be fetched. See, g t naught. So this will be multiplied with g t naught, g of t. So at t naught, whatever value of g will be there, that will be fetched. That is what we represent it as, g of t naught. And when you take its integration, it will result in 1. So ultimately, you get the value as g of t naught as per the sampling properties of fifth property, part 1. I have written it once again. X of t into delta of t minus t naught will result in x of t naught delta of t minus t naught. Just understand here. If I just put an integration of it, x of t naught, you take it common, integration of delta t minus t naught into dt will result in area is equal to 1. 1 into x of t naught will result in x of t naught itself. These are the two parts of the properties phi, property phi. So to illustrate it, I have taken few more examples here. Please consider here, x of t into delta of t minus 3 will result in, check the part 1 property phi. X of t, delta of t minus t naught. In place of t naught, I am having 3. So just write it as x of 3, delta of t minus 3. That's it, because I don't have integration here. Similarly here, x of, it is nothing but t minus of minus 2. So hence the value of t naught is minus 2. So I write x of minus 2 delta of t plus 2. Similarly here I am having integration. So x of 10 integration of delta of t minus 10 will result in 1. 1 into x of 10 is x of 10 itself. This is the answer. Similarly here it is nothing but t minus of minus 5. Hence I get it as minus 5 integration of delta. It will give you area is equal to 1. Hence it is x of minus 5. Very important definitions and illustrations of unit impulse. So with this, we'll move on to the next property, that is scaling property. The scaling property, to write it in simple manner, I write it here, delta of at times scaling will result in 1 by a into delta of t. This is what we need to prove. For that, we have just here, t naught is 0 actually in this case. We'll get the same thing if I put t naught is equal to 0. If t naught is there, in general we need to consider t naught. So this is how it looks. This property, I've taken the same definition here. Delta of at is equal to 1 by a into delta of t. To illustrate it, I'll take one of the references that I had mentioned in the previous slides. Delta of t is equal to limit delta tends to 0 x delta of t. X delta of t looks like this. The width being delta, the height being 1 by delta, that is amplitude. Its area delta into 1 by delta will give you 1. So this illustration I have already provided to you. Now I'll take its reference to move forward. Delta of at will give me time scaling is equal to limit delta tends to 0 x delta of at. Here also it will be time scaled by e. It is nothing but compression. If this compressed, I told you while explaining the time scaling and time shifting, so you have to divide by the factor, timing factor or scaling factor, to the time axis, minus delta by 2a plus delta by 2a. That is what is written here. So if I check, delta by 2a plus delta by 2a will give you 2 into delta by 2a, 2 cancels, delta by a. Delta by a is a width. Now delta by is a width. I want to maintain its area to be 1. But here it has become delta by a. Initially its amplitude was 1 by delta. So to make area is equal to 1, to make strength is equal to 1, what extra thing I need to add is into a, or the amplitude should be raised to a by delta to keep its area constant. So now when width becomes delta by a, amplitude becomes a by delta. That is what you need to understand here. So hence, limit of delta tends to 0, a into x delta of at. A into x delta of at means x delta of at is here. Time scaled. I am amplitude scaling with into a. This is in extra I am adding into a here. So this gives me what? Area is equal to 1. If area is equal to 1, what we call such signal? It is an impulse signal. It is a delta function. That is what is written here. That is what is written here. So now a, I'll take it out. A into limit a delta tends to 0, x delta of at will result in delta of t. This a I'll take on the right hand side. So what do we get? We get the same thing what has been asked here, 1 by a delta of t. If we consider in general, rather than t not equal to 0, if I have any other value, you just write, we replace t with t minus t naught. T minus t naught here, t minus t naught here. That's the answer for the scaling property of the impulse. This is time scaling property. I hope it is clear. Now we will arrive at the last property of the impulse. Derivative of an impulse is given by delta superscript of 1 in the parenthesis of t is nothing but differentiation of delta of t. Differentiation of delta of t. So here, if I integrate it, minus infinity to plus infinity x of t, if I multiply it with the derivative of the delta, it is called derivative of the delta. Derivative of the delta of t minus t naught dt, then what we get is, without this derivative, what would we have got? We would have got it as x of t naught. That is what is the property number 5. X of integration of x of t, delta of t minus t naught would have resulted in x of t naught. Now I have a derivative, hence you write it as d by dt of x of t naught. Now we know that it is a constant. So when you differentiate the constant, you will get it as 0. So that's why this is not the way to do it. The meaning of this is, first differentiate x of t, then substitute t is equal to t naught. That's how you need to do it. The meaning of this is, differentiate x of t with respect to d of t, and then substitute the value t is equal to t naught for the outcome what you have got after the differentiation. If t naught is equal to 0, what do I got? X of t delta of t dt. So d by dt of x of 0. So this is a constant we know. So what we have to do? D by dt of x of t you need to take first, then substitute t is equal to 0 to that respective value. That's it. So here you should be very careful in substituting the value of t is equal to 0. So first you need to take its derivation or derivative, and then you have to substitute the value of t is equal to 0. So with this, we are coming to an end of the properties of impulse function. Now we'll move on to the next topic, that is the unit periodic impulse. This is a periodic impulses with period t. At every t it is getting repeated. At every t it is 0. At t it is getting repeated. 2t it is getting repeated. So like that. So you can decide on it. See, if I have something in suffix, for example, I write it here. Delta 1 of t is equal to what? This is nothing but summation n is equal to minus infinity 2 plus infinity delta of t minus n. In place of t I have 1, so I just don't write it, t minus n. That's the meaning. Means whatever value of n you produce here from 0, 1, 2, 3, so that particular impulses will be produced. For example, n I supply n is equal to 0. If I supply n is equal to 0, what do you get? Delta of t you get. If I supply n is equal to 1, you will get delta of t minus 1. If I supply n is equal to 2, you will get delta of t minus 2. If I supply n is equal to minus 1, you will get delta of t plus 1. So everywhere you will be having impulses. Okay, and at what time intervals you will be having? At every t, and t will be decided by us. Here it is 1 means at every 1, 2, 3, 4 like that. This is called impulse train. It is not pulse train, impulse train it is. Impulse train. So remember this, delta subscript 1 of t is nothing but summation n is equal to minus infinity to infinity delta of t minus 1. Lot of people confuse here while reading the subscript and superscript. If I write superscript in parenthesis, it is derivative of delta of t. And when I write subscript like this, the meaning is summation n is equal to minus infinity to infinity delta of t minus n capital T, or whatever you write here, 1 or 1. So please understand the difference between these two things. The periodic impulse is a sum of infinitely many. That's the meaning. Now quickly we go on to the next function, that is unit ramp function. So unit ramp function, we have two kinds again, continuous time signal as well as discrete time signal. The ramp signal is shown here. It is having unit slope. Slope is equal to 1, and This is also given by delta of u of lambda d lambda, which is again is equal to t is equal to u of t. Let me make this meaning clear to you by this diagram. So ramp function is given by it is 0 when t is less than 0 and it is t when t greater than or equal to 0. Means if t is equal to 0, amplitude is 0. If t is equal to 1, amplitude is 1. If t is equal to 2, the amplitude will be 2. So like that it proceeds. That's why I have written it as t. Okay, so this is a unit step. It is right taking the step at t is equal to 0 and at t is equal to, so it is all these are unit step function. All these are unit step function. Now what I am doing is I'm taking the running integral. It is a running integral from minus infinity to t. Please understand the meaning of running integral. T changes every time. Okay, so if t is equal to minus 1, t is equal to minus 1, I don't have any signal at all here. Okay, if you take integration of 0, you'll get it as 0. That's why you have written it as 0. So at t is equal to 1, if you take a running integration, this is the area under the curve that we need to compute. The meaning is at t is equal to 1 means minus infinity till 1 u of lambda d lambda you need to compute. So this is minus infinity to 1, you have 1 into d lambda. So you'll get it as whatever value 1, I'll get it as 1. So that is what I am writing here. So when t is equal to 3, this becomes 3. This becomes 3. So when it becomes 3, this becomes 3. That's the meaning of this. Okay. Or else you can simply write it as t into u of t. U of t is nothing but u of t exists for only t greater than or equal to 0. So either you can write in this fashion or else simply you write t into u of t. Both means the same. Now, the unit ramp function in discrete time signal looks like this. R of n is given by n for any value n greater than or equal to 0 and 0 for n less than 0. This is how it looks. For n equal to 0, amplitude is 0. For n is equal to 1, amplitude is 1. 2 for 2, 3 for 3, 4 for 4, 5 for 5. And for negative axis, it will be 0. How it is written in the other way? R of n is equal to n. For only n greater than or equal to 0 means u of n exists only for n is equal to greater than or equal to 0. So its amplitude is 1. Hence 1 into n will be n itself. So rather than writing in this fashion, you can also prefer this way of writing. So that's a unit ramp function. Okay, so this is one more kind of the signal called ramp function. Now we move on to the other important signal for study in elementary signals part. The first being the Signum function, the second being the Sinc function. Signum function also exists in continuous time as well as discrete time. Signal function you say is written as sgn signum. Sgn of t is given as the value of Signum function amplitude is minus 1 for t is equal to less than 0. For t less than 0, amplitude is 1, minus 1. And for t is equal to 0, amplitude is 0. It's taking transition, but we write it as 0. For t greater than 0, amplitude is 1. So at 0, it's a transition point. It's a transition point. If I ask you to write the amplitude for t is equal to 0 of a Signum function, so you have minus 1 also, 1 also. Okay, so that's why we prefer it to write it as 0 because it is transiting. There will be some delay, so it will be overlapping, it will be crossing through the 0, hence we write it as 0. Similarly, for discrete time signal, Signum function is written as minus 1 for n less than 0 plus 1 for n greater than 0, and for n is equal to 0, it is 0. So here it is amplitude 0. There is no amplitude at all. For minus 1, minus 2, n equal to n values, you have amplitude minus 1. For n greater than 0, your amplitude is plus 1. This is Signum function. Now, Sinc function. We had taken this Sinc function analysis for analyzing energy of the Sinc function. Energy or power of the Sinc function. So here we are understanding the Sinc function. Sinc function is given by sine of pi t divided by pi t. The graphical notation or representation of the Sinc function will look like this. Sinc function, main lobe, side lobes, and it goes on decreasing time axis across the time axis. At t is equal to 0, the amplitude is 1. How to compute it? So at t is equal to 0, if I substitute, sinc of 0 is equal to sine of pi into t is 0, pi into t is 0. Sine of 0 is 0, 0. 0 by 0 is not a number. So hence what you need to do? You need to compute its amplitude. So 0 by 0 is not an accepted form. So you need to consider L'Hospital's rule in this scenario. L'Hospital's rule. Yeah, what does L'Hospital's rule says? In this case, what you need to do is limit t tends to 0. As t tends to 0, what is the function for our analysis? Sinc of t. So what you are supposed to do? Limit t tends to 0 sine pi t divided by pi t. So it will result in 0 by 0 form. Hence we should apply a differentiation of numerator and denominator. That's what L'Hospital's rule says. So if I differentiate and then substitute t equal to 0, if I differentiate it, I'll get cos of pi into t into pi. If I differentiate this, I get it as pi. Pi cancels. If I substitute t value is equal to 0, cos 0 will result in 1. That is what has been written here. Okay, sinc of t at t is equal to 0 is 1. This is how it is computed. So now we'll take up few examples before we conclude this session. So the first example being y of t is equal to r of t plus 1 minus r of t plus r of t minus 2. Before that, we first go on writing r of t. What is r of t? R of t is ramp function. It is a ramp function. So ramp function is written as, this is t axis, slope is 1. Means at t is equal to 1, your amplitude is 1. At t is equal to 0, your amplitude is 2. Like that. That is the meaning of slope equal to 1. So now I consider first term, this as second term, this as third term. Now first term, r of t plus 1. How it is written? This is time axis. So t plus 1 is nothing but shift the original signal to the left by 1 times. Left by 1. So left means this signal I'll take it on the left. I start from minus 1. See here, from 0 to 1, amplitude 1 I am having. From minus 0 to 1, the amplitude should be 1. Exactly shift by 1 time here. And then proceed in the same manner. This is also slope equal to 1. This is first term. Second term is minus of r of t. This is r of t, negative sign. This is t. So this is a positive slope. Just take the negative slope. That's it. Slope is minus 1. That's it. Rest everything is same. So at t is equal to 1, you have minus 1. At t is equal to 2, you have minus 2. That's how it goes on. And for third term, r of t minus 2. So how it is written? Shift right by 2 times. Take this original signal, shift 2 times. And whatever is happening at 0, it will happen at 2. Slope equal to 1. So these are the 3 signals that has been taken into consideration. So now here at 3, what will be your amplitude just for analysis? It is 1 because it is shifted by 2 times. Now I'll change the ink for the writing the answer. So y of t is a resultant signal. So if I take the sum of all these things, three things, we'll get y of t. This is time axis. So I start from minus 2, minus 1, 0, 1, 2, 3, 4. Okay. So now you can see these 3 terms. There are no signal values for the t is equal to less than minus 1. See here, there is no signal value. So up till here, it is 0 itself. From minus 1 onwards till 0, I am having only this signal. There is no signal here. From minus 1 to 0, there is no signal. From minus 1 to 0, there is no signal. Hence, just trace it in the same fashion. The amplitude is 1. Now from here onwards, it is getting added. Minus I have already taken care, it is getting added. It is rising with a slope equal to 1. It is decreasing with a slope equal to minus 1. From 0 to 1. From 0 to 1, it is rising with slope 1. It is decreasing with slope 1. slope 1. It has not yet appeared. So in the same manner, in what manner it is rising, increasing, in the same manner it is decreasing. Hence, these two effects will be nullified and the signal maintains the constant DC level. Up till where? Up till it appears, the next signal appears. Next signal is appearing at 2. So these two signal will add and will result in the same answer up till you get the value of the third signal. So here till here it is amplitude is 1 itself. Because it is positive slope, it is negative slope, both effects are cancelling and it is maintaining same DC level, constant level. And here for these two effects, it is maintaining constant at amplitude 1. There is one more signal getting added, that is with slope equal to 1. So this is like a DC level now. This is a variation. So for this, if you add this one, so it will result in slope equal to 1 ramp signal here also, thereon it continues, here also it continues. So this is the output of the given signal. We will take up one more example. Second one, x of t is given by r of t plus 1, r of t, u of t minus 1, 2 into u of t minus 2. So first I write r of t plus 1. This is being faster. So I don't write r of t, or else I write it here. R of t is nothing but it is unit slope from 0 onwards. Slope is equal to 1. So t plus 1 is, in the previous diagram we have already shown. So it is slope 1 starting from minus 1. Here it is 0. Its amplitude is 1 here. And it continues similarly in this fashion. And for minus r of t, this is first term. Second term being minus r of t. It is negative slope. So at 0 it is 0, at 1 it is minus 1. I just mark it for your understanding. It goes on. Slope is minus 1. Similarly, for u of t minus 1, third term, u of t minus 1, this is unit step function. Shift u of t by 1 time onto the right. That's it. It continues. And then u of t minus 2. Let me write u of t minus 2 first here. 0, 1, 2. Shift u of t minus 1 looks like this. U of t minus 2 shifted by 2 times. This is how it looks. But there is amplitude minus 2 for it. Hence the fourth term it is. Fourth term minus 2 u of t minus 2 is written as, this is just for rough work. This is written as, this is t, 0, 1, 2, 3 continues. Here this gets amplitude minus 2. Amplitude minus 2. Minus 2 amplitude. This is minus 2 into u of t minus 2. Now we will write the resultant signal with a different ink. Resultant signal is x of t. This is time axis. I write from minus 2, minus 1, 0, 1, 2, 3, 4. It continues. Till minus 1, you just check. Till minus 1, the value is 0. There is 0, 0, 0. So till minus 1, the value is 0. From minus 1 to 0, this exists, this doesn't exist, doesn't exist, doesn't exist. Trace it in the same manner. Amplitude 1. From 0 to 1, 0 to 1, slope 1, 0 to 1, slope minus 1. So hence it nullifies and constant arises. 0 to 1, 0 signal, 0 to 1, 0 signal. So this effect and this effect will be nullified and you will get a DC constant of amplitude 1. And from 1 to 2, 1 to 2, slope 1, slope minus 1 from 1 to 2. So these two will result in the constant DC. But here at 1 to 1, I am having amplitude 1 signal. So for this amplitude 1 signal should be added. But from here 1 to 2 is not there. So 1 to 2 signal gets added because of this. So when it adds, already it is at 1. When it adds, the amplitude becomes 2. From 2 to 2 onwards, slope 1, slope minus 1, and it continues. All these three signals, it continues. Here, New amplitude is getting added by because of the fourth term, that is minus 2. So whatever value I'm having, minus 2, if I add to it, minus 2 into plus no, minus 2 plus 2 is 0. So it continues thereafter. That's it. So this is the answer for the given problems. So two examples in the similar problem, say a similar way, we can solve a number of examples. So we'll look into more number of problems if possible in the next session, and we shall start with the next section of the topic of this chapter number 1 of signals and systems. We shall start with what is a system and properties of a system. With this, we are concluding today's lecture. Thank you one and all.